Now, rather than a point mass on the end of a string or massless rigid rod, let's imagine we've got some extended object and we want to support this at some point, and we're going to let it swing back and forth like this. So rather than just a point mass, we've got something more complicated. We could also imagine supporting this at a point not even within the object, so that it's swinging like this. And again, we have a more complicated type of pendulum, but still referred to as a physical pendulum. So what's the difference between this and what we had before? Well, rather than a point mass, let's now imagine that we've got something more complicated, some complicated shape, but again, it's supported somewhere within the object. It doesn't have to be. But now this distance L, rather than the distance from the point of support to the point mass, let's imagine this is the location of the center of mass. So wherever the center of mass of the object is, the distance from the origin to the center of mass, we'll call that some distance d. Okay? So wherever the center of mass is, wherever the point of support is, the distance between those two we call d. Now notice that in this case, my center of mass, let's see, where is the center of mass? So the center of mass would be right around here. If I were to try to support this from the center of mass, so I put a little hole here. It's a little easier said than done. I'm trying to stick a paper clip, which is not sharp, through this cardboard. Okay, give me 1 second. There we go. If I support this from the center of mass and I displace it, I guess I didn't quite get it at the center of mass. So let's see, center of mass should be a little bit lower. But I think you can imagine that if you support it from the center of mass and you turn it, it's not going to oscillate at all. If I could actually get this at the center of mass, it's only close. But the closer you get it to the center of mass, if you rotate it, it's not going to oscillate at all. It will just stay there. So when d is 0, then you really don't have a pendulum at all. All right, so what happens in this case? Well, again, let's look at the torque. What is the torque? The force is still going to be the weight, mg, so the torque will be, now d, assuming the weight acts at the center of mass, it's going to be d times the force, mg, times the sine of the angle between them, and again, it's going to be sine theta, and a minus sign. And again, let's assume we can use the small angle approximation, so we'll call this theta. And this must be I alpha. But now, what is I? What is the moment of inertia of this thing about that point? Well, it's not just ml squared. We can use the parallel axis theorem. We know that the moment of inertia about this point will be md squared plus I center of mass. So the moment of inertia is not just md squared, it's going to be larger than that by an amount of the moment of inertia about the center of mass. The idea is that if this thing is rotating like this, we can think of that as two motions. It's going like this, but also like this, rotating about the center of mass, like this. So there's two parts of the moment of inertia that have to be taken into account. That's what makes this a little bit more complicated. So we'll just leave this as I, and then this is equal to I times d squared theta dt squared. In other words, d squared theta dt squared plus dmg over I times theta equals 0. And then what we have is, rather than m over L, we end up with this more complicated quantity here, dmg over I. Okay, so what's the period now in this case? Let me just put it all together. We end up then with t is equal to 2 pi root, and again this thing just flipped upside down, I over mgd. Okay? Notice that if we turn this into a simple pendulum, then we know I is equal to md squared, ICM would be 0 in that case, and notice the m's cancel, one of the d's cancel, we get root d over g, or L over g. We get the same thing back for the simple pendulum. Okay, so that looks good. It gives us back what we expect for a simpler case. Now, one more thing. Let's go back to our idea of the oscillator. If we could actually set this up, and imagine we had this on a frictionless surface as much as possible, well, maybe not exactly possible, and I started this oscillating and we came back later, what would we expect? Well, we would expect this to have eventually stopped moving, basically because you can't really have a perfectly frictionless situation. It would eventually stop moving. So how can we take a real situation into account? How can we add perhaps some friction into the solution? What would happen if we did that? Well, let's take a look. For a perfect system, like an ideal spring with no other forces acting on the mass, we would have an oscillation that looks like this and just keeps on going forever and ever. But in a real situation, or something at least a little bit closer to being real, what we would have is something that would get smaller and smaller as it oscillated. It could get smaller very quickly, or it could get smaller more slowly, but something like this, where the amplitude of the motion seems to decrease. How can we take something like this into account mathematically? Well, the easiest way, or one very easy way, is to say that there is some friction acting on the system, and when we talk about a harmonic oscillator that has friction, we say that the oscillator is damped. We refer to the friction as damping. And the easiest form of a damped frictional force is to say that the damping force is proportional to the velocity. So what we'll say is actually it's going to be proportional to the velocity and opposite the direction of the velocity. So whatever the direction is, the frictional force is acting back in the opposite direction. However it's moving, the frictional force is trying to slow it down. So we have a negative term there, and to make these proportional, I will put in a constant of proportionality called B. Okay, so B is telling us the relationship between the velocity and the frictional force. So what's this going to do to our differential equation that we had describing the motion? Let's take a look at that and see how we might go about solving it. Our equation of motion now becomes the force, the total force, will be minus kx, the spring force, and then plus the minus bv, there's the damping force. And that must equal, F equals ma. So dividing by m and bringing these terms over on this side, divide everything by m, we'll have a plus b over mv plus k over mx equals 0. Using the fact that a is the second derivative of position with respect to t, and v is the first derivative of position with respect to t, we have d squared x dt squared plus b over m dx dt plus k over mx equals 0. We expect the solution to this, in other words, what's x as a function of time, we expect it to look something like this. But what's the mathematical form? How can we describe that? Well, let's guess something. By looking at this, let's guess what the solution might look like. We expect x as a function of t to still have some cosine dependence. So we expect some cos omega t plus delta, but the omega might not be the same as the omega that we had before without damping. So we'll call this omega prime t plus delta. Again, the delta is in there so that we can start it at any point on the oscillation. We've got the cosine oscillatory part, but notice the amplitude seems to be decreasing. The amplitude seems to follow some kind of exponential decrease. So let's say that the amplitude then is something like a e to the minus gamma t. So here's our amplitude, and we notice that it is decreasing exponentially, e to the minus gamma t. And then here's the oscillatory part, that's the part going up and down. Okay? Let's see if this doesn't work. Well, how are we going to do that? What we're going to do is we're going to take this and put it into this equation. We'll differentiate once to get dx dt, differentiate that again to get d squared x dt, stick it in this equation, and set it equal to 0, and let's see what we need to do to make that equal to 0. Well, to tell you the truth, that's a bit of a mess, a mathematical mess when you differentiate this, so I'm going to do it off camera, so to speak. I'll put the result up here, and then we'll take a look at what the conditions are, and let's see. Okay, this is what we get. The position, remember, we are letting equal a e to the minus gamma t cosine omega prime t plus delta. Differentiating that, we've got two terms with a t in it. We've got the exponential and we've got the cosine. Differentiating the exponential brings down a factor of minus gamma. So dx dt is minus gamma a e to the minus gamma t cos omega prime t plus delta. And then differentiating the cosine gives us a minus sign with a factor of omega prime. So we have minus omega prime a e to the minus gamma t sine omega t plus delta. Then differentiating that to get d squared x dt. Again, we've got two terms. We'll differentiate the exponential, bringing down another factor of minus gamma. So we have gamma squared a e to the minus gamma t cos omega prime t plus delta. Differentiating the cosine brings out another factor of a minus with an omega prime. But over here, when we differentiate the exponential here, we'll bring down a minus gamma, which gives us the same term here. So we end up with 2 gamma omega prime a e to the minus gamma t sine omega prime t plus delta. And then leaving us over here, differentiating the sine over here, brings out another factor of omega prime and turns this into cosine. So we have minus omega prime squared a e to the minus gamma t cos omega t plus delta. There we go. So that is d squared x dt squared. And then what do we want? We want d squared x dt squared plus b over m dx dt plus k over mx. So d squared x dt squared, we've got the three terms from right here. 1, 2, 3. And then plus b over m dx dt. So we take this multiplied by b over m. We have minus gamma b over m, blah, 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 minus omega prime b over m, a, e, blah, 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 blah. And then plus k over mx. So plus k over m, and then x, a, e to the minus gamma t cos, blah, blah, blah. And then all of that equals 0. Phew, there we go. Now, we need to simplify this. How are we going to do that? First of all, notice that every single term has a factor of a e to the minus gamma t. So we're going to factor off an a e to the minus gamma t. When can we do that? As long as a e to the minus gamma t is not 0. In other words, a to the minus gamma t cannot be, e to the minus gamma t cannot be 0. As long as a is not equal to 0. So we're not going to look at some constant solution where x equals 0. That's not a particularly interesting solution. We're not going to consider that. So we're going to assume a e to the minus gamma t is never equal to 0. So I won't cross it out. I'll just erase it. Well, I don't want to confuse us here. So dividing off a e to the minus gamma t, 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 a e to the minus gamma t. There we go. Now what we notice is we have some terms that are cos omega prime t, and some terms that are sine omega prime t plus delta. What I'm going to do is gather up all the terms that are cos omega prime t plus delta and all the terms that are sine omega prime t plus delta, and I'm going to write those with 2 coefficients from all of the coefficients of those terms. So hold on one second, back again.